Hello everyone, I'm Syed Mukit Hossain from University of Technology Sydney and I'm pursuing my PhD under the supervision of Professor Ho Kyung-sung. Today, the title of my presentation is Facile Synthesis of G8-Induced Electrode for Selective Lithium Recovery from Aqueous Solution by using Capacitive Deionization System. For lithium, the only way is up if you consider the demand. For instance, only the contribution of electric vehicle is expected to show a demand growth of 35% by 2030. Add to that the mixed growing demand from diverse battery-based technologies. Comprehensive economic analysis showed to meet the substantial high demand, lithium production must be quadrupled by 2030. Now, if we look into lithium sources around the world, lithium deposits come in three main types. There is rock containing lithium, clay containing lithium, and salty water or brine that contains lithium. So, conventionally, to get lithium out of the rocks and clay, you have to use various chemicals and processes. When it comes to lithium brines, the conventional way is to pump the brines into huge solar evaporator pond and let the sun evaporate the water, leaving the lithium salt behind. Although solar driven, this method is slow, inefficient, and unsustainable. So our group is interested in the next generation direct lithium extraction or DLE techniques. As the name suggests, instead of using evaporation, lithium is directly extracted from the brine while returning the water to its original source. This method has several advantages over the conventional methods, such as smaller carbon footprint, rapid and efficient process, and substantial reduction of chemical and energy use. So here we have proposed an environmentally friendly simple method called capacitive deionization or CDI for direct lithium extraction from seawater. This method has several advantages over the conventional DLE methods. As you can see, in conventional CDI, saline water passes between a pair of porous electrodes, which are usually carbon-based. While your working voltage is applied in between the electrodes, the salt ions in the feed flow migrate to the electric double layer at the carbon-water interface, which performs the desalination. So we plan to utilize the same mechanism for selective lithium extraction. However, the bare carbon electrodes are not very selective towards lithium. Recently, a number of works claimed that metal organic framework subclass called GIF8 can promote lithium selectivity by permitting only lithium to cross over in a solution. Hence, we plan to use a thin film of GIF8 on our activated carbon electrodes to make it selective towards lithium. On this slide, you can see the experimental layout of the study. The CDI cell we used is a plexiglass mold with a spacer separated 10 into 10 centimeter electrode system. We have performed the electroabsorption experiments in batch mode and analyzed the kinetic variation in ion concentration of the model solutions. Moreover, we have used equimolar binary model solutions with lithium competing ions like sodium, potassium, magnesium, and calcium. Here you can see the boundary conditions of our study. Now, here you can see the modification route of the SA electrodes. We have synthesized two types of modified electrodes, one with only GF8 coated AC electrode and the other is cation exchange membrane or came over GF8 coated AC electrode. So for GF8 coating, we have used water-based rapid in situ growth of GF8 on the electrode and later casted commercial chem layer using casting blade method. So from the ACM and EDX results, you can see the successful formation of GF8 on AC electrode. Although in general, the shape of GF8 is usually that of diamond dodecahedron. However, here you would say a mixture of diamond and spherical form. This phenomenon was primarily brought on by the fact that the differential rate of evaporation of milky water that occurs during in situ development of GF8 brings about some degree of variation in the intensity of the solvent. It has been observed that during the process of crystal development, a change in the polarity of the solvent generated a distinction in the amount of saturation that occurred. In future, adjusting the morphology of GF8 might be done with the help of this technique by changing the type of solvent. Moreover, we have observed that single coat of GF8 was not enough to cover the whole surface of AC electrode. Hence, we doubly coated the AC electrode and then cast chem layer on the surface. In addition, both XRD and FTIR analysis also confirmed the formation of GF8 on the AC electrode successfully. Now, if we look into the performance results, so here before coating means the performance of the commercial AC electrode. So while we ran the CDI at 1 volt of voltage in a binary solution of monovalent sodium and lithium, we have found sodium removal of around 26% and lithium removal of 18% after 12 to 15 minutes to get the electrode saturated. So from the results, you can see it's not very selective to lithium. However, after the GF8 coating on the surface, if you look into the results, the sodium removal reduced to around 7% and lithium removal increased to 21%, which definitely show a substantial increase of relative lithium selectivity. So for monovalent sodium, we have seen a substantial increase of lithium selectivity. So same pattern we have observed for monovalent potassium also. So in a binary mix of potassium and lithium, while we ran the CDI cell for the feed water at a voltage of 1 volt, we have seen a potassium removal of 24% and lithium removal of 11% before the GF8 coating. But after the GF8 coating, the potassium removal reduced to 12% and lithium removal increased to 14%. So there is also increase in lithium selectivity. However, for the divalent ions like magnesium and calcium, we haven't seen any improvement in relative lithium selectivity. As you can see here, for the commercial AC electrode in binary mix of magnesium and lithium, the magnesium removal was around 36% and lithium removal was around 24%. However, after GF8 coating, the magnesium removal reduced to 19% and lithium removal also reduced to 13%. So the selectivity didn't change much. However, the removal reduced. Same pattern we have observed for calcium also. So before coating, the calcium removal was 32% and lithium removal was 18%. And after the G8 coating, the calcium removal reduced to 28% and lithium removal to 14%. So we have also assessed the performance of the G8 and chem coated electrodes. So here you can see the variation in results. So again, for chem coating with G8, we have seen substantial improvement in lithium selectivity after in case of monovalent ions only, and for divalent ions the lithium selectivity remained similar or somewhat reduced in some cases. So here you can see before the G8 coating in commercial chem electrode, the sodium removal was 43%, which reduced to 26% after the G8 coating, and lithium removal was 39% before coating and remained around 37% after coating. So there is a good increase of lithium selectivity. Again, for potassium, before coating, the removal was 46% and lithium removal was 45%. After coating, potassium removal reduced to 30% and lithium removal to 36%. There is also an increase in lithium selectivity, which was not the case in case of divalent magnesium and calcium. And now, if we look into the selectivity trend of lithium in the piston electrodes, so you can see for the AC electrode, the selectivity reduced while the competing ions were in the sequence of sodium, magnesium, calcium, and potassium. On the other hand, for the commercial chem electrode, the sequence was sodium, potassium, magnesium, and calcium. Perhaps the high charge density of lithium played a part in case of increasing the selectivity a little compared to the AC electrode for the commercial chem electrode. However, in all cases, the lithium selectivity was well below 1. So after the modification of G8 in the AC G8 electrode, the selectivity increased quite a lot for the monovalent sodium and potassium, which are 3 and 1.12 respectively. On the other hand, for G8 induced chem electrode, the selectivity of sodium and potassium were well above 1, but not as much as the AC G8 electrode. The values were 1.38 for sodium and 1.12 for potassium. For the mechanism, from our observation, we have proposed that due to the low hydration energy and a small ionic diameter, mainly lithium is crossing over the G8 coating while monovalent ion is competing and contributing to the current flow. So in the figure, you can see the partial hydration-dehydration based crossing over mechanism of lithium ions. However, the presence of divalent ions as competing ion, the lithium selectivity did not increase as much. Overlapping of the ideal of S electrode and GIF along with high charge density based Coulombic attraction may have contributed substantially. Hence, in presence of magnesium and calcium as co-ion and the chem layer, the relative lithium selectivity remained minimal. Let's see some challenges. So, considering the limited stability of G8 in an aqueous solution, all the performance and selectivity results reported in this study are performed by using a single-use G8 coated electrode, and replicating the experiment did not show any morphological change on the electrode. However, as you can see, a CDI runoff 10 hours showed a substantial change in the morphology of ACG-fed electrode. Additionally, we have not observed any leaching of zinc in the effluent through ICP-MS. A leaf-like structure was observed on the surface of the used ACG-fed electrode, which is also reported in a number of previous work. In literature, it has been reported that after 4 hours of exposure to water, GFAD starts to hydrolyze into derivatives of zinc oxide and eventually completely changes after 72 hours of exposure to water based on the wet ratio. Finally, although GFAD promoted lithium selectivity in our electrode, there are a number of challenges to overcome. For instance, the low stability of GF8, non-uniform in situ growth, and integration of GF8 framework with monovalent selective cation exchange membranes. So, which are the future aspects we are working on? Thank you for your attention.